Welcome everyone. Today we'll explore about assuring flexible pipe integrity, inspection, monitoring life extension, ensuring durability through advanced inspection and monitoring. Overview of flexible pipe integrity management, agenda and key focus areas. Flexible pipe integrity management is a structured, lifecycle approach designed to ensure that flexible pipes operate safely and reliably throughout their service life. These pipes are complex, multi-layered structures combining polymer and metallic components, which makes their integrity management challenging. The process involves aligning design considerations, operational practices, inspection routines, and monitoring strategies to mitigate risks. Key threats include corrosion, fatigue, wear, and chemical ingress, all of which can compromise performance if not properly managed. Integrity management frameworks typically employ risk-based methodologies, where probability and consequence assessments guide inspection intervals and monitoring priorities. This approach ensures that resources are allocated efficiently to address the most critical threats. The ultimate objectives are to prevent loss of containment, maintain structural capacity, and achieve a LARP, as low as reasonably practicable, risk levels. By integrating data from inspections, sensors, and operational records, integrity teams can continuously update threat registers and adapt plans to evolving conditions. This proactive strategy not only safeguards assets but also optimizes operational uptime and reduces costly interventions. The presentation will cover 5 major areas. Number 1, a brief introduction to flexible pipe integrity management. Number 2, inspection of flooded annulus and its impact on pipe integrity. Number 3, inspection of wire armor and associated risks. Number 4, current integrity and condition monitoring methods. And number 5, approaches to flexible pipe life extension studies. Each section will provide practical insights into why these aspects matter, how they are assessed, and what actions can be taken to mitigate risks. The agenda is structured to first establish foundational knowledge, then delve into specific failure modes and inspection techniques, followed by monitoring strategies and finally life extension considerations. This logical flow ensures that participants understand the interdependencies between design, inspection, and operational decisions. By the end of the session, attendees will have a clear understanding of how to integrate inspection findings with monitoring data to make informed decisions about maintenance and life extension. The goal is to equip stakeholders with actionable knowledge that supports safe, cost-effective operations. Flooded annulus and its impact, wire armor inspection and integrity assessment. The annulus in a flexible pipe is the normally dry space between the pressure sheath and outer sheath, housing armor wires that provide tensile strength. When water ingress occurs, due to outer sheath breaches or end-fitting leaks, the annulus becomes flooded, creating a corrosive environment for armor wires. This condition accelerates degradation through uniform corrosion, pitting, and crevice corrosion, especially when oxygenated seawater is present. The consequences include reduced tensile capacity, increased fatigue susceptibility, and potential catastrophic failure if left unchecked. Inspection strategies for flooded annulus involve vent port checks for moisture and chemistry, visual assessments for sheath damage, and advanced techniques like thermography to detect cooling signatures indicative of leaks. Acoustic or ultrasonic screening and borescope inspections at end fittings provide further evidence of wetting and corrosion. Understanding the rate of corrosion requires evaluating oxygen availability, temperature, and chemical composition, which influence degradation speed. Findings from these inspections feed into engineering assessments that update residual life calculations and inform mitigation measures such as drying, sealing, or operational restrictions. Armor wires are critical load-bearing components in flexible pipes, responsible for handling tension and hoop stresses. Their integrity is vital for structural performance, yet they are vulnerable to corrosion, fretting, and fatigue, particularly in dynamic environments with vortex-induced vibrations, VIV. Inspection of armor wires is challenging due to limited access, but several techniques are available. Visual and borescope inspections at end fittings provide initial insights into corrosion or wear. Electromagnetic methods such as magnetic flux leakage, MFL, and low-frequency eddy current testing, LFED, detect section loss, while ultrasonic guided waves and alternating current field measurement, ACFM, identify cracks and surface defects where geometry permits. Metallurgical sampling may be employed during cutbacks for detailed analysis. Once inspection data is collected, engineers translate findings into quantifiable metrics such as metal loss per wire and the number of affected wires. These inputs update structural models to reassess tension capacity and fatigue life. Decisions on repair, replacement, or enhanced monitoring depend on risk evaluations, operational constraints, and economic considerations. Current integrity and condition monitoring techniques. Condition monitoring complements inspection by providing continuous or periodic data on operational and environmental parameters that influence pipe integrity. Key metrics include top tension, internal pressure, temperature profiles, and dynamic motion data, which are essential for fatigue analysis. Annulus condition monitoring involves measuring vent gas flow, moisture content, and chemical composition, O2, CO2, H2S, as well as annulus pressure trends. Structural health indicators such as acoustic emissions, strain gauges, and vibration sensors offer insights into stress and potential damage initiation. Monitoring tools range from annulus monitoring skids equipped with moisture and gas sensors to clamp-on inertial measurement units, IMUs, for curvature and VIV tracking. Advanced systems like distributed temperature sensing, DTS, and fiber optics provide granular thermal data, while digital twins integrate real-time measurements with analytical models to predict fatigue usage and annulus risk. The ultimate goal is to transform raw data into actionable intelligence through a risk-based integrity management, RBM, loop, acquire data, assess conditions, decide on interventions, and update threat registers. This iterative process reduces uncertainty and enhances decision-making. Flexible pipe life extension assessment and deliverables. Life extension studies are initiated when operators seek to prolong field life, defer replacement, or operate under new conditions. These assessments require a structured approach to demonstrate continued integrity. The process begins with consolidating all relevant data, including design specifications, operational history, inspection records, and deviations. Threats such as annulus flooding, armor wire degradation, and fatigue usage are re-evaluated against current conditions. Analytical models are updated to reflect metal loss, corrosion rates, and dynamic loading scenarios, incorporating sensitivity analyses to address uncertainties. Mitigation plans, such as enhanced monitoring or operational restrictions, are developed to manage residual risks during the extension period. Deliverables typically include an integrity status report, updated operating limits, a time-bound inspection and monitoring plan, and contingency strategies for repair or replacement. These outputs provide clarity to stakeholders and ensure that life extension decisions are evidence-based, balancing safety, reliability, and economic considerations. By following this rigorous workflow, operators can confidently extend asset life while maintaining compliance and minimizing risk.